Hello everyone. Today we're going to work in coding the travel assessment problem. This is our first example with integer variables. Particularly, we're going to be using binary variables. So we're going to be coding this model that I have here on the left. It's one of many ways of modeling the TSP problem. Basically, what we're going to do is that given a certain number of cities, and in this case, we're going to position this series randomly in a square of 100 units of side, and we're going to solve the TSP for that instance. So let's do that. So we create a new class. I'm going to call it TSP. Right. So we will be solving this for a given number of cities. So we need to be given the number n. So given that, we are going to generate a random position for the 100 cities. So we're going to do random data first. So the X position, the array for the X position. Okay, so here the array has size n, but you gotta remember that in Java the arrays goes from 0, it starts from 0, so particularly this array is going to be from 0 to n minus 1, right? So in our problem we have stated from 1 to n, but in Java they're going to be labeled from 0 to n minus 1, so just keep that in mind while we're doing the code. So for y is the same thing. Now let's fill those arrays. So we iterate through I, excuse me. Okay, so this function gives you numbers between 0 and 1, and we multiply them by 100, and then you get numbers between 0 and 100 with a uniform distribution. Same goes for y. Okay, so that's the random position, and now we're gonna generate the Cij matrix. Okay, that is gonna contain, for this case, the Euclidean distance between all of the cities. So this matrix has, C has 2 dimensions. And we need to iterate through I and j this time. We need to fill the whole matrix. So the Euclidean distance, so this is going to be the square root of the summation of the square of the difference. Okay, so the difference of the x coordinate, so it's going to be I minus the x position of j. plus, and now the same thing goes but for the y's. So y minus, yeah, this to the power of 2. Alright, so that's Euclidean distance. So we're done with the random data. So we generate a random matrixCij's, okay, given the n cities. So let's do the model now. Okay. So we need to import the library. Gonna use it like that, and surround it with the try and catch. Okay, variables now. So we have two kinds of variables here. We have the xij's, which is binary, and we have the ui's, which is because it's continuous from 0 to infinity. Let's do x first. X has 2 dimensions. X is n by n, but here we need to leave empty the last dimension. When we are defining the variables, the last dimension we're gonna declare afterwards. We can't do it like this, so that's why we always leave the last dimension incomplete. And we need the concert library for this. One of these will do. So let's take care of the last dimension. Okay, so the xi, which is the previous to the last dimension. Okay, so to define the last dimension, which is where the variables are actually placed, we need to use the CPLEX instance that we just created before. And here we tell the model that we're gonna be using binary variables. So this is meaning Boolean. That tells CPLEX that the x is gonna be binary, between 0 and 1. It's just 0 or 1. And the size of this array is gonna be n. Okay, so at this point we created the x variables, which is a variable n by n. Okay, and let's do u now. Okay, so u has only one dimension, which is the last one. I mean, the first, the only one that it has is also the last one. So we directly use CPLEX to define it. And these are n variables. It goes from 0 to infinity. Right. So there we have the variables. Let's do the objective now. So I define an expression, and I create an instance using the CPLEX instance we created before. Okay, so now the objective is empty. The expression is empty, so let's fill it up. So we're going to be creating this first one here, the objective, which is the double summation of theCij's, Xij's. So we need to iterate through I and then through j. Okay. And here the j has to be different than I in order to make the summation. So we add that. So only when it's different. Only when it's different. There. So we take the objective and we add a term, which is going to be theCij's multiplied by the Xij. Okay. So here constantly is adding up the multiplication betweenCij's and Xij's. Okay, so at this point, the objective is what we want it to be. But so far it's just an expression. CPLEX has no clue that this is the actual objective, neither that it has to minimize it. So we need to do that. And there we have it. Now the objective is being really established. Let's do constraints now. Okay, so the first constraint is for each j. So first thing here we do is iterate through j. So for each j, we're going to create an expression. All right, so the expression is going to be the summation through the Xij's that considering that I is different than j. Okay, overall i's. So we iterate now through I. And I has to be different than j. So now we accumulate the Xij to make the summation. So we add the term. And it's going to be a 1 because it doesn't have any constant there. So it's just a 1 multiplied by the Xij. Right. So while still being within the loop for the j, we're going to add the constraint, which in this case is an equal. And on the left hand side is the expression, and this is going to be equal to 1. Okay. So for each j, we create an expression which then we fill up with the summation. We do it directly in the inner loop. And then once we finish with the inner loop, we add this, we add the constraint. And we do that for all of the j's. And very similar is the case for the second constraint we have here. So I'm just going to copy this Now make the proper changes. So for each I, then we're gonna make this match for each J, and the J has to be different than I. It doesn't matter how the order here in the if, but I'm just gonna make sure that it's the same as in the model. And that's it. So there we have the second constraint. All right, let's do the last constraint. The last constraint is for every I and every J, and doesn't consider the first city. Okay, remember that our first city here in Java is 0 instead of 1. So instead of starting the for loop from 0, we're going to start it from 1, and in that way we're going to be omitting the first city. And we do the same for the J. And also the I has to be different than J. Okay. So this is that combination there. So within this combination, we create one constraint. So we create the expression here, and we build it. So as a 1 multiplied by the UI is going to be a -1 multiplied with the uj, and a n-1 and -1 multiplied by xij. Okay, so same level that we created the expression, we have to put the constraint. So it's going to be CPLEX that, in this case, is a less than equal constraint. Okay, so less than equal what? The expression. The expression that's represent the left hand side, and this has to be less than equal than n minus 2. Okay. All right. This is it. We have the variables, objective, and the constraints. We need to solve the model now. And we do it by calling solve method. And then we need to clear up everything here. So just for the sake, turn everything. Right. Okay, this should work. Let's see if it does. All right. I'm forgetting something here. So I'm running it from this side, and here I have the example for last week. So I need to put the PSP. So okay, let's do what, 25 cities. Okay, there we go. So this is what we want. Here's the branch and bound process. The interior solution that I find on the way of finding the optimal, and the lower bounds. And in the labs column, you have the relative gap. So if you wanted to play a little bit here, we can do more cities, and we're going to see how much time it's going to take to do that many cities. And all right, so the TSPS and NP-hard problems is going to take a lot of time if you put a lot of cities. And here you can see how much slower it is with 100 cities. You see how it generates. This is the size of the tree that is generating. And depending on the number of cities, you can sit around and see how it solves, and sometimes it can take, depending on the numbers, it can take days of solving. All right, so that's it for now, and for the next video, we're going to continue doing in this same problem, and we're going to be playing with some tuning that we can do, some post-processing, and the solution pool. We will be also doing, coding how to stop the branch and bound earlier, so that we waste so much time waiting for the optimal solution. Right, that's it. See you next time.